Okay, folks, welcome. This is going to be a big experiment, so please bear with us.
Okay, folks.
We've never done this before.
Okay, folks, welcome.
There we go.
This
See?
is going to be a big experiment, so please bear with us. Okay, we've never done this before. Okay, folks. There we go. See?
All right, that's just about that down. So yeah, thanks for coming in, everyone. I see about 70 participants right now on the YouTube live stream.
So yeah, thanks for coming in, everyone. I see about
Okay, hopefully I managed to kill all of that. Yes, so thanks for coming in, folks. We're very lucky to be able to do this. I know that for probably a lot of you, things are pretty up in the air right now. It's a real pleasure to be able to try to do this in spite of all the disruptions right now. For those of you who've never attended one of these, my name is Brian Jackson. I teach physics and astronomy at Boise State in the physics department. And this is our first Friday astronomy lecture series. For those of you who have never attended one of these before, they usually take place in person. So I'm sorry we're doing this online, but hopefully it'll work out okay. The way that these work is on the first Friday of every month. So that is the first Friday of every month. Today is the first Friday of April. On the first Friday of May, June, July, we will host a guest lecturer. That person will discuss their space science research. Sometimes that's space policy. We've done astronomical mythology before, so it takes kind of a wide variety of things, but focuses on space and astronomy. So that guest will come in and speak about their work for about an hour. And then when we do these in person, we do stargazing on campus. Unfortunately, of course, we can't do that remotely. So for now, we're just going to have the lecture portion. And my plan is to live stream these talks the way we're doing now, probably over YouTube in the future, until all these disruptions end. So for now, be prepared for some live streaming. We are fortunate that we have a pretty full schedule already arranged for the summer. Here you can see the poster for our summer session. So we already have all of our summer slots filled out. And so we'll have guests come in and do these lectures probably online for the foreseeable future, but eventually, again, we'll do these in person. Starting in May, for instance, we'll have Dr. Kelsey Crafton. She's a public policy fellow at the American Astronomical Society, and so she's going to tell us a little about space policy. In June, we'll have Professor James Evans from the University of Puget Sound. He's an expert in ancient astronomy, and so he's going to tell us some really fascinating things about something called the Antikythera mechanism. I'll let you Google that and find out what that is. He's an expert in that. Professor Catherine Devine from College of Idaho will visit us in July to discuss star formation. And then we'll have Dr. Paul Verhage, who teaches math and science at the Treasure Valley Math and Science Center. He does some really fascinating experiments with suborbital ballooning. And so he's going to give us some talks about that work. So we're going to have a really full summer here. Should be a lot of fun. So at these live stream sessions, the way we're going to work is there's a chat box in the top right-hand corner of the YouTube stream. So if you're observing this lecture on my website, the thing to do is to click on the title of the live stream at the top of the YouTube window, and that'll take you to the YouTube live stream. And then you should be able to see a chat box on that YouTube live stream, and you'll be able to ask questions of our guest speakers in the chat window. So I'm going to type something into the chat window right now. That will require you to sign in. So hopefully you have some kind of Gmail account, some Google account. But if you have such an account, you'll be able to sign in and ask questions of our speaker that way. And the way I want to run these questions is I'm going to let you ask questions throughout the talk, and then I'll try to keep track of the questions as we go along. And I'm going to relay them to our speaker at the end. Okay. So with that, I want to do an introduction for our speaker here. We may be having an audio issue. So let me see what I can do about that. I will say that the YouTube live stream is about 20 seconds delayed. And so if you get a sense that there's a little bit of a delay there, that's because the live stream is about 20 seconds behind where we are in real time. So give me just 1 minute to try to address this audio issue, and we'll be back on, and I'll introduce our guest speaker, Professor Devin Burr. Can you hear me?
Can you hear me now, Brian?
Oh, there you go. Perfect. You got it. There you go. That's perfect. Great. Okay, let me introduce our guest speaker. Everyone else is just seeing a blank screen right now. So I'm back on the feed here. Perfect.
Oh, there you go. Perfect. You got it. There you go. That's perfect. Great. Okay, let me introduce our guest speaker. Everyone else is just seeing a blank screen right now. So I'm back on the feed here. Perfect. Oh, perfect. You got it. There you go. That's perfect. Great. Okay, let me introduce our guest speaker. Everyone else is just seeing a blank screen right now. So I'm back on.
Okay, Devin, I'm not sure if that was me or you. You're gonna have to shut down all the other streams you have. If you have the window open somewhere else with you don't. Okay, so maybe that's me. I don't seem to have it up anywhere else. Okay, let me unmute you. I've got you muted right now. Hang on 1 second. Let me unmute you. I'm gonna mute myself.
I did shut down my YouTube video.
That's it. Yes, that's what was causing it. Yeah, it's very tricky. Okay, great. Let me just. Okay, I'm gonna pin myself. Here we go. Perfect. Okay, so folks, thanks for coming in. We're very fortunate to have with us this evening Professor Devin Burr. Professor Burr is an associate professor in the, excuse me, she's Professor Burr is at the Northern Arizona University's Planetary Sciences and Astronomy program in Flagstaff, Arizona. Before joining Northern Arizona University, Professor Burr was a professor at the University of Tennessee in Knoxville. Professor Burr earned a PhD from the University of Arizona's Geosciences program, studying outflow channels on Mars. Before that, Professor Burr earned a master's degree in geology and then a master's degree in philosophy. And then before that, Professor Burr was at the Naval Academy in Annapolis, Maryland. Professor Burr has a wide variety of interests, primarily in geomorphology. And I think tonight we're going to hear some very interesting things about rivers across the solar system. And so with that, Professor Burr, I think if you share your screen, that should bring up your presentation. Perfect. Okay, and I'm going to mute myself, and you just roll along with your presentation. I've asked folks to enter questions in the chat window on YouTube, and so I'll relay those questions to you at the end, if that's okay.
I'm happy to take them in real time, Brian. Just if someone's like, I don't understand this term and I keep using it and I should explain it in real time, then I'm more than happy to be interrupted.
Great. I'll try to do that. I'm not sure how well that's going to work just because of my trying to manage things all at once. But if there does seem like a really pressing question and things that seems like it won't interrupt things too much, I'll go ahead and relay a question to you.
That would be great.
Great. Thank you.
Thank you, Brian, so much for putting this together. And I think I was mishandling things a bit on my end. I appreciate your patience and getting this up and going for us. I'm excited today to talk about rivers across the solar system. We have rivers on Earth, of course, and they have a variety of channel patterns. For this talk, I'm really going to focus on just the two most common channel patterns. The image we see on the left is a braided channel pattern. I don't know, I guess maybe you can't see my cursor. So the river is this entire gray width in between the pine trees on either side. But the threads within that river weave in and out together or have a braided appearance. So we call this a braided channel pattern. Now this pattern is distinct from a meandering channel pattern, where there's a single river, a single conduit for water that's maintained within the banks. On the left, again, we have multiple conduits for water and they're interconnected or braided together. And on the right, we have this single conduit for water. And that single conduit for water kind of winds its way over the landscape. And we call this a meandering channel pattern. It derives its name from the Meandros River in Greece, of all places. So those are the two channel patterns that I'm going to focus on for this talk, braided and meandering. Now, meandering rivers are common on Earth. This is another example of a meandering river. It's on the north slope of Alaska. And at the lower left, you can see a scale bar of 100 meters. We can see the river. Again, I'm sorry that I can't show this to you with a cursor, but we can see the river stretching from the middle right.
Devin, we can see your cursor, just to give you a heads up. We can see your cursor.
Oh, sweet. Beautiful. That's what I needed. Thanks, Brian. So the river stretching across the image from the lower right to the upper left. And then we can see these kind of loops here that are also filled with water. And those loops are the previous location of the river. This meandering river is actively migrating laterally back and forth across its floodplain. And when one of those active meanders gets cut off, it leaves a lake, one of these curved lakes, and we call those lakes oxbow lakes. This is a cartoon of a device that's used on oxen to harness them to pull loads. And I guess our ancestors thought that these curved loops here maybe looked something like this harness for oxen. We have a meandering river and it's left some oxbow lakes on its floodplain. Another example of meandering rivers from the Amazon. This is this beautiful image where we can see these large curves. And we can see places again where there are these oxbow lakes, where the river previously inhabited, but since cut off its loops. And we can see right down here in the foreground where the river is just about to cut off this loop also and leave a relic oxbow lake. Right now it's still flowing through there, but any moment it's going to cut off this loop and we'll get another oxbow lake here. So that's what meandering rivers look like on Earth, and they're common on Earth. To form a meandering river, the banks, plural, have to have some cohesion, some stickiness, some strength in order to maintain the water in a single channel and not have the water spread out and form a braided channel pattern. So here's a cartoon of a meandering river. And in this bottom part of the cartoon, the direction of time is going from left to the right. And we can see how the river starts out moderately, relatively straight, and becomes moderately curved, becomes more curved, and eventually the river breaks off this neck here and becomes straight, and we get this oxbow lake. We're familiar with that by now at this point in the presentation. So here's a river that's meandering, and we see this cut bank here, and that refers to the place where the river is cutting into the bank. The bank has to have some cohesion. Otherwise, if the river were cutting into the bank and the bank had no strength or no cohesion, then the water would just overflow the bank, and we would end up with this braided pattern. So this is what happens when, instead of the bank providing some resistance, the river is able to overflow it and create multiple channels, multiple threads. So again, just to remind ourselves, this is an image of this beautiful braided river in New Zealand. This width here is the entire width of the river, but then there are multiple braided conduits or threads within that river. And in contrast, going back to the Amazon, this is what a meandering river looks like, where there's a single conduit or single thread that transports water. Okay, so we understand now that meandering rivers require some bank cohesion, or they transition into a braided pattern. On Earth, we think this cohesion or this stickiness or this strength of the bank comes from the vegetation. So why do we think that? Well, we have data, first of all, from the rock record. As we look back in time, we see a coincidence in time between deposits that look like they were laid down by a river and rooted plants. Here's a diagram showing that coincidence. The symbology termed meandering up here refers to sediments that seem like they were laid down by a meandering river. LA sets refers to lateral accretion sets, and that is the structure of those sediments as the river is migrating laterally, moving laterally back and forth across its floodplain. So these first two are both evidence of a meandering river. And then the third symbology up here is for rooted plants. And we can see that in general, there's a correlation that we first see evidence for meandering in the rock record about the time that we see evidence for rooted plants in the rock record. The Devonian era, which is the era of the fishes, that stretches from about 400 million years ago, give or take. Okay, so this plot shows us some data that suggests a correlation in time between meandering rivers and rooted plants. We also have theory This is a complicated diagram. Let me walk you through just one branch of it. The theory goes that if we have an absence of vegetation, so before we get rooted plants on Earth, then we have an absence of roots, right? Vegetation has roots, so no vegetation, no roots. If we have no roots, then there's less binding of the bank sediments by the roots. That means the bank sediments are lower stability. And if the bank sediments are lower stability, that means they can't resist when water impinges on a bank. And that allows the river to develop a braided river style, a braided channel pattern. So we have data on the right, we have theory on the left as to why the cohesion or the stickiness or the strength of banks that's required for meandering rivers comes from vegetation. But it's a little bit imprecise. We see this evidence here in the rock record for meandering before we see evidence in the rock record for roots. I mean, this is just a few tens of millions of years, right? Among friends, I mean, maybe that doesn't matter. But now we see evidence for meandering river deposits on Mars. This is not Mars. This is back on Alaska. I just want to remind us what meandering river deposits look like on Earth. This is what we see on Mars. The two images are to approximately the same scale. They both have 100-meter scale bars on them. We've walked through the image on the left. Let's walk through the image on the right. The illumination from the sun is from the left. So this is a ridge because the sun is shining on one side and then there's a shadow on the other side. So this is a positive relief ridge winding its way across the image. And the red arrows at the bottom point to this ridge. And then on either side of this ridge, we can see these wonderful loops. Here's a nice loop. Here's a nice loop. Here's a bit of an irregular loop. Here's a lovely loop. Here's another loop. So we see, just looking down on the landscape, we see the same elements on Mars that we see on Earth, which is to say we see a river stretching across the landscape and then these loops on either side of it. Likewise on Mars, we see this ridge that winds its way across the landscape and we see these loops on either side of it. So we see the same elements, the same pattern. We have just one small problem, which is on Earth, a river is a trough. It's negative relief. And the image that I'm showing you, that I'm asserting boldly, is a meandering deposit on Mars, is a ridge. It's in positive relief. So how does that work? All right, well, let's take an aside and talk about terrain inversion and how it works on Earth and on Mars. This image on the right is, of course, of Earth. It's of the Stanislaus Table Mountain, which is 2 hours or so east of Sacramento in Northern California. What we see in this image is a brown line, a brown ridge stretching across the image. The sun is coming from the right and there's some shadowing on the left. So this brown line is a ridge. There's some streets, some highways for scale. This ridge, this Stanislaus Table Mountain, formed about 10 million years ago when there was originally a river in this location. But then a volcano, a few tens or 100 kilometers or so up north of this image, erupted some lava into this river valley. The lava filled the river valley. You can actually see a little tributary of that river valley down at the very bottom of the image. The lava filled the river valley. Then 800 million years later or so, we got a glaciation period. And during that glacial period, a larger portion than normal of Earth's ocean water was tied up in glaciers or in ice caps. that meant that the elevation of sea level dropped. And when sea level drops, that causes rivers to be more erosive than normal. And the landscape on either side of this table mountain, on either side of what was a river valley filled with lava, the landscape on either side of this river valley filled with lava got eroded, but the lava was resistant to this erosion. And as a result, this linear lava deposit was inverted into positive relief. So on Mars, we think we see the same elements. There's a river. Somehow it dries up and becomes more resistant to erosion than the surrounding landscape. The surrounding landscape gets eroded, and what was the riverbed is now a positive relief ridge. So it's the same principle, but there's some minor differences in exactly how that occurs. So again, we start out with a river. The river dries up. It fills in with sediment on Mars. We don't think it's lava capping. We think there's just sediment deposit in the river. Then on Mars, there's a deposit of material that preserves the landscape, that buries the landscape and preserves it. Then eventually, we have a lot of time to work with wind on Mars. Mars has been dry and windy for something like 3.5, 3.8 billion years. That's a long time for the wind to work. Then the wind erodes this layer. That's what aeolian abrasion means. It means wind erosion. And it erodes this layer and it leaves the river deposit in inverted relief. We see evidence for this eroded layer, this eroded burial layer in these landscape features that we call yardangs, which is an Arabic word that means ridge. All right, so let's look at a landscape on Mars and see how this works. So here at the top are some yardangs. These are remnants of what was a burial layer, a layer that covered this landscape, but has gotten eroded by the wind. And we can see that this yardang material sits on top of this platform, of this layer. And in this layer, we can see another one of these thin, winding ridges stretching across the landscape. And so it's this thin, winding ridge that we interpret as an inverted river deposit that was protected from erosion by this overlying layer. So that's the fun story on Mars as to why we think we see meandering river deposits, because they look just like meandering river deposits on Earth, only they have this minor detail that they're in positive relief, but we think we can explain that. What we are not sure we can explain is the cohesion on Mars. What provides the cohesion or the bank strength that's necessary to form meandering rivers? To investigate this question, my colleagues and I went to a meandering river on Earth that does not have rooted plants around it. So we went to this area in the Black Rock Desert of Northwest Nevada. That red box covers approximately this area that's shown in this black and white aerial photograph. This is a 0.5 kilometer scale bar. The dark ribbon winding its way across this image is the river. And we can see some of these lovely loops that we've come to understand characterize meandering rivers. We can see some of those on either side. And this is a smaller river that's coming in to join this larger river. So we can see, just looking at this aerial photograph, that this river is indeed meandering. It's moving back and forth across its floodplain, and it's leaving these oxbow lakes behind. This is what it looks like from the ground. You can see that there's not very much vegetation. There is some, but the roots are very shallow. This is Yo Matsubara, who led this work for us as part of her dissertation thesis, her dissertation work. So to get from the road into the campsite, we had these wonderful horses take us in and some dogs and people. Here's our water. We set up camp after about a 2 or 3 hour horse and people trek. The horses were carrying our stuff. We were trekking. We set up camp, and the next morning we got up and we went to the river, and this is what the river looks like. It's got this big bank in the back. You can see how steep this bank is and how tall. This is what we would call a cut bank, a term we saw earlier in the presentation, where the river is cutting back into the floodplain. You can see from the height of this bank, my colleague here is about 6 feet tall. You can see from the height of this bank that if the bank did not have strength or cohesion or stickiness, it wouldn't maintain such a high angle here. It would collapse. So there must be something in this bank giving it cohesion. And we knew that because it's a meandering river. Okay, so what is it that's giving it cohesion? Well, our hypothesis going in, our best guess, our idea that we were exploring was that clay was giving the bank strength or cohesion. We all know that clay is sticky. You can walk through sand and it'll wash off, but if you walk through clay, then it gloms onto your shoes, right? Really sticks to them, weighs them down. We can see from the bank closest to us, we can see these desiccation cracks that form in clay. We can see an old channel here where the river has worked its way across the floodplain and reoccupied. The river was apparently coming in and out of this bank. Now it's going parallel to the bank. And in that bank, we can see some kind of grayish light material, which is clay. And here's an image where I've walked across the river. There's some more desiccation cracks in clay here. And you can see that I have clay about up to my knees. So not many roots, plenty of clay, a good place to test our idea that clay can provide cohesion that promotes a meandering river channel type. Well, our fieldwork, the results of our fieldwork supported our hypothesis that clays can provide bank strength. So without going into too much of the science details, I'll just point out this image where we can see clay draping the shores of the river, and we can see what look like pebbles, but are in fact clay nodules. It's where clay is stuck together. And if we look at some of these deposits under very high magnification, we can see that they're all draped with clay. All this light tone in this image is a shallow covering of clay. This is 1/10 of a millimeter. All right, so we inferred that clays in this region in this river on Earth are providing bank cohesion, and we have clays on Mars. This image shows a number of different mineralogies that are derived from water or produced by water. Phyllosilicates is a kind of complicated term for clays. So anywhere where there's blue, we see clayey material. We've seen clayey material in remote data, in orbital data from Mars orbiters. And so you can see there's just a lot of blue on this global image of Mars. So there might be even more blue than we can see, because we can see in some cases that some of these materials maybe are superposed on these blue dots. But the takeaway message from this image is that there are a lot of clays on Mars. Clays form in the presence of lava that undergoes aqueous weathering. Lava plus water commonly produces clay. The image that I showed you early on was from this location on Mars. And you can see there's a lot of lava around this location. Here is that image that I showed you early on. So our feeling is, our interpretation is that the meandering planform, the location here where there's a lot of lava, the fact that there's a strong topographic gradient here that would have promoted precipitation, that all these factors came together to produce these inverted meandering deposits, and that their cohesion came from clays. So this box here in black, I'm showing on the left of the screen here, is this area now in this box. And what we actually see in this box is just this wonderful menagerie of different types of river deposits. I should have replaced the word fluvial with river up here. I'm sorry about that. We see this wonderful range of river morphologies, of river shapes in this area. This is what we've been talking about so far in this presentation, where we see a ridge and then we see these beautiful loops on either side of it that we interpret to be oxbow lakes. But we see other things too. We see these other ridges that have tributaries in them, and these other ridges that come together and then fan out again. And we interpret all of these as formed by flowing water. So this is just a beautiful area on Mars that we love to explore. We have rivers elsewhere in the solar system that exist today. What I've been talking about on Mars are rivers that are river deposits. They came from rivers that are billions of years old. But there is one other planetary body in our solar system besides Earth that has rivers forming today, and that's Titan. Oops, excuse me. Titan is the largest natural satellite, the largest moon of Saturn. In this image, you can see this is Saturn in the background. We have Saturn rings here. And this is an image of what Titan looks like. You can see in this image that Titan has a thick atmosphere that's largely opaque at visible wavelengths. We can't see through it at visible wavelengths. But we do have data from the surface of Titan, and they're radar data. And I'll talk a little bit about that when we look at those data. Now, to have rivers, you have to have an atmosphere. So check, we've got that. And that atmosphere has to rain. It has to produce precipitation. Precipitation is produced by clouds. And here we see a 3-image sequence: forming, moving, dissipating, forming, moving, dissipating, forming, moving, dissipating. Clouds that form, move across the image, and then go away. And this image sequence was interpreted early on when it was first seen as clouds that formed, rained out onto the surface, and then dissipated. We have other evidence that there's rain and surface liquids on Titan, and that's in the form of what look like lakes on Titan. This is a lake on Titan. This is radar imagery. So what we're looking at here is dark area. Dark means smooth in radar. Bright means rough. So what we interpret this image to be showing us is a lake with a relatively smooth surface and rougher terrain around it. This lake is called Ontario Lacus. It's roughly the size of Lake Ontario. And for comparison, we have also in radar imagery, we have the Etosha Pan, which is in Namibia, which also is filled seasonally with water. And so if we look at both of these in radar imagery, we can see kind of a tonal analogy, a tonal similarity between them. So we have evidence from the atmosphere and evidence from the surface that there are liquids on the surface of Titan. Where do we get these data from Titan? Let's talk briefly about the Cassini-Huygens mission. The spacecraft, the Cassini spacecraft, was named for Giovanni Cassini, who actually, though he was an Italian, he worked in Paris and used the name Jean-Dominique Cassini. So here is this billion-dollar spacecraft. And it's got this, this attachment on the left that's covered with gold looking foil. And that attachment was the Huygens probe. And that probe was named for Christian Huygens, who was a Dutchman who, like Cassini, did early work on the Saturnian system and made discoveries for us about the rings, for example. So this is just an artist's sketch of the Cassini-Huygens spacecraft. Again, the spacecraft itself is called Cassini, and then there's this Huygens probe on the bottom of it. The Huygens probe was launched from the Cassini spacecraft, fell through the atmosphere, and landed on the surface of Titan. All right, so the data we're looking at come from the Cassini-Huygens mission. Well, what do they show us? They show us river networks that look like rivers, look like river networks. We're looking again at radar imaging on the right. So dark is smooth, commonly a lake. So this is a lake. And this dark winding ribbon is interpreted as a liquid formed channel. We also have some bright winding ribbons that stretch across the landscape. In this image, this bright area at the upper right is interpreted as bright because it's rough, because it's a mountainous region. And these bright threads that come out of this mountainous region are interpreted as rivers draining the mountains. And they're bright because they have cobbles, rocks in their channels. So we have this variety of river-formed morphologies. We've talked about just a couple as an illustration. We can map them out and analyze. It looks like my image got cut off at the bottom. I'm sorry about that. And we can analyze the networks and see what kind of a network morphology they have. One thing, we have a lot of dendritic network morphologies on Earth. Dendritic just means branching, like a tree. On Titan, we found a lot of rectangular river networks. So this is what the rectangular river networks look like. They have a lot of right angle bends and a lot of straight segments. They form on Earth less commonly than dendritic networks, but when they form on Earth, they're associated with faults in the subsurface. So we were really excited to discover this suggestion that there were faults on Titan, and to discover it in this unusual way through looking at the river network patterns that we can see on the surface. Now, I mentioned that these bright ribbons here that come out of this mountainous terrain are bright because they have cobbles in them. So this is some work showing that these bright channels are brighter than they should be in radar. And the interpretation is that the cobbles are very nicely rounded and larger than the wavelength of the radar in order to essentially focus the radar energy back to the spacecraft. So they act as reflectors, these rounded cobbles. And this is what we see from the Huygens probe that landed at the surface. This is a different location on Titan than these rivers, in these river beds, but it supports the analysis that these river beds are bright because they have rounded cobbles in them. Because here in this one image from the surface of Titan that we got from the Huygens probe, we can see some rounded looking cobbles that are indeed a few times the wavelength of the radar. So, oops, that didn't work too well. So how does this happen on Earth? Well, let's look briefly at how cobbles move in rivers. So we're going to dive below the surface here, and we're going to see that cobbles are bouncing, sliding, or skipping along the bottom. They're fairly rounded. They don't have any sharp corners on them. This rounding probably happened way upstream. But this video suggests how the rounding occurred. It occurs through impact in the river. It chips off the angles or the corners or the rough edges, and it produces these more rounded. We get to hear how noisy it is on the bed. Okay. Should be able to move on now. All right, so what we've tried to do based on these two different lines of evidence, the analysis of those two bright channels and the image from the surface of Titan from Huygens probe, so these two different lines of evidence that there are rounded cobbles on Titan, we've tried to simulate that rounding process in the lab. So we've used a roller mill. And if any one of you had a rock polishing device as a child, I did. You put rocks in it, you put some grit in it, you turn it on, you come back a day later and you have these beautifully polished rocks. That's essentially what a roller mill is. It's a type of erosion experiment that lets us see how rounding occurs. The image we were just looking at from Alaska, obviously that was rocky material. On Titan, the material is ice. Crust of Titan is created of ice. And so we simulate the rounding of river cobbles on Titan by putting ice cubes into a rock polishing device, essentially. So on the left here is graduate student Tony Maui working with me on this project, and Joe Levy at Colgate University, who very skillfully created our first Titan tumbler, as we call it. So Tony and Joe are creating the ice cubes to put into the tumbler. We made ice two different ways. One is we just froze the ice in the ice cube trays. The second, which is being illustrated here, is that we crushed the ice in a snow cone machine that Joe bought for us with NASA dollars off of eBay for 60 bucks. And we crush the ice in a snow cone machine, then we pack the ice into the ice cube trays, and then we flood that ice with water, and we create something of an icy sandstone. Then we take those cubes and we put them in our tumbler. Here's a schematic of what the tumbler looks like. Let me see if I can get it. Yeah, great. So here's a video of the tumbler in action. Now we're trying to simulate conditions on the surface of Titan. Titan is 10 times farther away from the sun than we are, which means it gets 1 over 10 squared, or 1 over 100 times the energy from the sun that we do. So it's very cold. The crust of Titan is ice. The liquid flowing in the rivers is liquid methane, which is a gas, of course, here on Earth. So to simulate that temperature, we've got this Titan tumbler spinning in a bath of liquid nitrogen. And this tube here is dripping in a constant drip of liquid nitrogen into this bath. And then the nitrogen comes up just about to this line. So that's what the Titan tumbler looks like from the outside. From the inside, these are the icy clasts. These look like not the sedimentary clasts. These are just the straight up ice clasts. And this is what it looks like when they're tumbling inside the tumbler. These white baffles inside the tumbler are designed to promote rolling. We don't want the class riding up on the side and then slamming down. That wouldn't be very similar to the impact or the shock or the pressure that the rocks observe or that rocks experience in a river. So we've got these baffles to cause the class to tumble. We can tumble them for a certain amount of time. We can estimate the travel distance, and that lets us estimate how round the sediment gets as a function of distance. We're just working on our first paper on this. Our initial results, though, suggest that icy sediment rounds approximately like rock, surprisingly. So here are some icy clasts before we put them in the tumbler, just straight out of the S-cube trays. This image down here shows the roundness values that they have, about 0.73, 0.68, 0.74. We put them in the tumbler, we get them back out, and this is after just half an hour, I think, not very long tumbling. We can see that the roundness values have increased, so they're rounder now, obviously, than they were. And we can see that with our eye, right? This data on the bottom, these data on the bottom allow us to quantify what we can see with our eye, which is that the sediment rounds. The rate at which it is rounding is not dissimilar. It's not perfectly the same because on Earth, different lithologies round at different rates. But these rocks, these ice rocks in our Titan tumbler round at rates that are somewhat similar to the way some soft rocks round in rivers on Earth as a function of distance. So we can infer based on assumptions about the input size, and those are just, or I'm sorry, input shape, and those are just assumptions. We can infer the minimum transport distances for rounded cobbles on Titan, and we're getting distances of a few to a few tens of kilometers. We're still working up the broader implications of this work, but we think we've got a neat approach here, and we're trying to improve our technology and address a couple of technological challenges that we're facing. All right, so we've talked about meandering river deposits on Mars that are in inverted relief. If we ignore that little issue, then, and we think we can explain that issue, then these look just the same shape as meandering river deposits on Earth. We think we know what provides the cohesion on Mars, and that is clay. We've looked at an analog river on Mars, so a river that looks like these deposits, an analog river on Earth that looks like these deposits on Mars. And we've used that to investigate the cohesion. And again, we think that substantiates the clay hypothesis. We've looked at some river networks on Titan, and we've discovered that a lot of the Titan networks are rectangular. That's red in this image up here, are the rectangular networks. And that had some interesting, some unexpected and fun implications for what's controlling the liquid flowing in the rivers on Titan, the liquid methane flowing in the rivers on Titan. And that is, we think there's some subsurface faults or structures controlling the river flow. And then we've talked briefly about some fluvial experiments that we're doing, trying to simulate river transport in these rivers that we can see on Titan. And from that, learn something about how to interpret the data we have about how rounded the rocks are, how rounded the cobbles are in the rivers on Titan. We think we have rounded cobbles. What can that tell us about the distance that they've been transported? So that's what I have to offer today. I thank you for your interest and your attention, and I'd be glad to take any questions.
I'll give you a hand, Evan. I'm the only one that you can hear right now.
Thanks, Brian. I can hear it.
Okay.
I can feel it.
Can you hear me?
I can.
Perfect. Sorry, yeah, we're on a little delay here, so you probably waited a little bit. Yeah, so we do have a couple of questions in the chat window here. The first question I think I saw, somebody asked about where did the rivers go on Mars?
Oh, what a great question. Yeah, let's see. Can I get back to that in real time? I guess I don't have a global image of Mars. So just in this region, for example, and for scale, this colored area is about the size of the state of Arizona, I realize that doesn't quite work so well for this audience, but anyway, even if you're not from Arizona, you can imagine the size of Arizona roughly, right? So for scale, that's about the area that we're looking at. And these rivers, we think, these ancient 3.8 billion year old rivers flowed into this depression. The cool color here is low. These warm colors here denote higher terrain. And the different colored lines denote the different river shapes or different channel morphologies, different channel types. So we see these rivers generally oriented around the margin of this depression, and we infer that the rivers flowed into this depression. The water probably went both up and down. So we think the water infiltrated into the surface and froze, perhaps there's some subsurface ice layer on Mars. We think also that a lot of the water went into the atmosphere. Mars has quite a thin atmosphere, and some in this audience know more about Mars' atmosphere perhaps than I do. Mars has an atmosphere that's only about 1/100th the density, the thickness of Earth's atmosphere. That's what it is today. 3.8 billion years ago, when there were rivers, it was probably a thicker atmosphere. It had to have been to have created these rivers. But that atmosphere has since been eroded away, removed, we think, by a variety of processes. One might be impact erosion, heating of the atmosphere due to impact and driving it off. One might be erosion by the solar wind. We have a mission at Mars right now called MAVEN. And I haven't kept up with MAVEN results. Maybe, Brian, you're more in tune with that than I am, since you think more about Mars atmosphere than I do. But that mission is helping us discover what happened to Mars atmosphere. So the short answer to the question is, where did the rivers go? Well, the water went either into the ground or went both into the ground and formed a subsurface ice layer, and it got evaporated into the atmosphere, and the atmosphere was subsequently eroded away.
Great, thanks, Devin. Another question about when volcanoes on Mars erupted. When did they erupt?
Oh yeah, great question. So we have two particularly large volcanic provinces on Mars, Olympus Mons here and Elysium Mons over here. And then there's some Tharsis volcanoes, 3 large volcanoes, shield volcanoes also here. Another one, Alpatera, a bit north. That's a great question. And the answer seems to be that they erupted over rather a wide period of time. The Tharsis volcanic bulge, which is Olympus, and then these 3 volcanoes over here that we don't see, that seems to have formed moderately early on in Mars history. So it's a few billion years ago. I don't know exactly, I'm sorry to say, so something like 4.2 billion years ago, 3.8 billion years ago. The fact that Olympus and the Tharsis bulge are on the equator suggests that these volcanoes formed early enough that they reoriented Mars, that they were such a large mass on the surface of Mars that they might have reoriented Mars so that they were at the equator, because that's a low energy state for a large mass on a spinning body. So the idea is that they formed fairly early on, but that the eruptions have continued. So we have lavas from them, and we have other evidence that resurfacing of those volcanoes continued maybe over 2 billion years or more. So the answer, when did they erupt? Probably over a long period of time, probably over a couple billion year period, from maybe 4.5 billion years ago up to just a couple billion years ago. And we have very young lavas too. The Cerberus lavas here are not volcanoes, but they are super young lavas. And we have some age dates on the Cerberus lavas of just a couple of million years ago. So the question as to when the volcanoes erupted was a couple billion years ago, but volcanic activity continued on Mars until just a couple of million years ago, which is rather amazing for such a small body.
Great, thanks, Devin. Another question, and let me see, I'm not sure I quite understand it, but I'm going to read it as best I can understand it. How do you know that, so this is in reference to your experiments on sediment rounding on Titan. And the question is, how do you know that that it is sediment and not ice chunks that are rounding?
Excellent question. I think I didn't do a perfect job setting the scene. Let me go back and set the scene. So here we are on Titan, 10 times farther away from the sun than the Earth, where water is as hard as a rock. And so the rocks on Titan are indeed ice. The crust of Titan is ice. So what we think of the surface of the Earth, the crust of the Earth as being rock. The surface of Titan, the crust of Titan is ice. So we are doing these experiments on ice, on water ice that we've cooled down to the kind of temperatures that we see on the surface of Titan. Nitrogen is liquid at, what is it, about 87 Kelvin, 90 Kelvin maybe. And so the surface temperature on Titan is about 94 Kelvin. And so we're using liquid nitrogen to cool this Titan tumbler down to Titan temperatures. And then we tumble ice rocks, kind of ice in air quotes, ice rocks or ice sediment within it. So if I'm understanding the question correctly, I think the questioner's got a great point. The rocks, in quotes, on Titan are actually ice, water ice.
Okay, great. Thanks, Devin. Let's see. What was the next question here? You made a comment that the river networks on Titan are rectangular. And then you said that tells us that they're probably related to faulting on Titan. Could you explain exactly how that works and how that contrasts with river channels on river systems on the Earth?
Yeah, I'd love to. Thanks for asking that question. I did skip over this a little bit quickly. The river networks that form on Earth, where there's a moderate slope and there are no heterogeneities, there's no resistance to flow in the slope. It's just picture a moderate hill slope covered with sediment, covered with soil. That's all the same thickness, the same grain size, everything's all the same. On a homogeneous landscape like that, dendritic morphologies, dendritic drainage systems are what generally form. And this image just shows two different renditions from two different papers as to what dendritic looks like. Again, dendritic means branching. And we use it to refer, for example, to the study of trees. We talk about dendrochronology, which is getting age dates on trees from green cores. So if we have a moderately sloping surface and a homogeneous covering on that surface, on that hill slope, on that landscape, we tend to get dendritic morphologies. And we see a lot of dendritic drainage morphologies or river networks on Earth. Rectangular drainage morphologies or network morphologies form, they're characterized by right angles or near right angles and sort of short tributaries. Near right angles, straight segments in between the angles and somewhat short tributaries. And these right angles and the straight river reaches form preferentially where there's something in the subsurface making them straight and causing the rivers to link together at right angles. A river doesn't naturally want to be straight, it naturally wants to meander. And we saw that early on in the presentation. So for them to be straight suggests that there's something in the subsurface that's causing them to be straight. And where we see rectangular or rectilinear networks on Earth, they're generally controlled by some kind of a fault system, some kind of a subsurface structure, like a tectonic fault that's causing the river to flow straight for some distance or to intersect another river at a right angle. We see them, for example, in places in Australia where the terrain is heavily faulted and the rivers have followed the faults that exist in the subsurface. It was a great question. I hope I answered it.
Yeah, that was awesome. I think that was really good. And I know this is strange for me to be asking you questions, and you can't even see the chat window, can you?
I can't, but I'm good.
Okay. These are actual, I promise, these are questions people are asking in your chat window. There's a question about the composition of the ice cobbles on Titan. Do we know that they're made out of water? Are they frozen methane? Are they made out of something else?
Yeah, terrific question. We are doing a very end member first order experimentation here, which is we're using pure water ice and we're tumbling the cobbles dry. Now on Titan, they're tumbling in a river. So you guys are saying to me, well, Devin, you know, there should be some liquid in there, and there should indeed be some liquid in there. We do have some experiments where we have some liquid in the chamber. I'm not showing those to you. I'm showing the dry experiments to you because frankly, the video was most intelligible. And we're using this pure water ice end member, whereas in truth, there are a lot of other compounds on the surface of Titan that contain carbon. In a planetological sense, we call compounds that contain carbon organic. It's not like organic in your grocery store. It's not related to life. It just means that they contain carbon. It's challenging from a safety perspective to include some of these compounds in our experiments. We see things on the surface of Titan like propane, butane, methane, acetylene, ethane. So things that are challenging to handle safely in an oxygen-rich atmosphere like we have here on Earth. Titan atmosphere doesn't have oxygen, so you know we'd be safe there, but it's a little bit tricky here. And we just haven't taken the extensive measures that would be required to introduce those impurities into our icy cobbles to make our experiments more realistic. That is something that we hope to do in our next round of experiments with some additional technological innovation. Great.
A question, if you don't mind taking, I have 3 more questions. Is that okay?
Absolutely.
Perfect. And then I'm going to let Professor Berg go because I know it's getting late there. Another question, why are the oxbow lakes on Mars not inverted the way the rivers seem to be?
That is such a great question. And if I knew the answer to that question, I would write a paper on it. I can't figure that out. And I haven't talked to any colleague that can really figure it out with me. We do see some that are slightly inverted. So here is what we interpret as the river trace. Here's what we interpret as an oxbow lake. You can see that the oxbow lake is a little bit inverted here. Here, the oxbow is a little bit inverted. But then we see other examples where they're not inverted, right? Where they're in negative relief out here on the floodplain. So some of them are a little bit inverted and some aren't inverted at all. And that's just a great question. I don't really understand the sedimentology there perfectly. It might be that the cementation process, or the process that made the riverbed more resistant to erosion than the surrounding terrain, than the floodplain, was mediated or controlled by the amount of water or some other factor that was greater in the river than in the Oxbow Lakes. Maybe more fresh water flowing through made the river bed sediments here more resistant to erosion than the sediments in the lake. And so when this whole landscape was eroded, the sediments in the lake were eroded more easily than the sediments in the river channel. That's kind of my best guess so far, but I haven't been able to come up with a precise mechanism to make that work. I've had a couple of other ideas that also are nothing more than ideas at this point. So I love that question, and I hope someday to be able to answer it. It was a great observation.
Yeah, that's a really good question. How did you become interested in this topic?
Well, I just think this landscape is beautiful. I got to talk earlier in this wonderful conversation earlier about how I choose my research topics. And I think everyone listening to me and looking at this can just see how beautiful it is, how graceful, how sweeping, how interesting and engaging. So I choose my research topics first, honestly, by what appeals to my sense of beauty, and then my sense of curiosity, and kind of go from there. So I just think these landscapes on Mars are just so lovely. Just these broad loops, these sweeping, graceful, meandering landforms, I just think are really lovely. And then after that, I get curious, and it kind of goes from there.
Yeah, that's awesome. Okay, and then the last question, probably the most controversial. Do you think that there is life on Mars, or was there ever life on Mars?
Terrific question. I think I'm agnostic on that. I certainly don't think that there wasn't life on Mars, but I don't necessarily think there was life on Mars either. Sorry not to have a more definitive answer there. It's one of those things that I don't really have data for it, so I kind of just withhold judgment. Trying to withhold judgment in general in life. So I can't provide a very meaningful response there. It's a great question. I don't have a good answer.
Great. Well, thanks so much, Devin. We really appreciate you giving the talk. And there's been a lot of enthusiasm in the chat window, so you've definitely got a very enthusiastic audience.
Well, it's super fun. I'm kind of getting into this mode now. You know, I'm like sitting in this dark room talking to myself.
Yeah.
But I can feel that people are listening and asking questions, and I love the material and I love sharing it, and I really appreciate people's attention and questions. So thank you to everybody.
Yeah, you did a great job, Devin. Okay, thanks a lot. Okay, folks, I'm going to go ahead and end the live stream now. Thanks for coming. Please join us again in May. That will be the first Friday of May. And we're going to have the next talk in May will be live streamed like this. Hopefully things will calm down by June and we can have these again in person. But if not, they'll probably be live streamed. Feel free to get in touch with me if you have any questions. And take care of yourselves. Stay well.